video lecture, we're going to talk about intermediate representation. And intermediate representation is something that is one step before we generate the assembly language for a particular instruction set. So let's say in the end, we are interested in producing x86 assembly language. We don't directly generate x86 assembly language from the abstract syntax tree in our code generator. Rather, we will write an intermediate code generator that produces what we call an intermediate representation. Advantage of an intermediate representation is that it provides an intermediate level of abstraction from the realities of an actual machine. For example, a machine architecture might have a certain number of registers, might have other constraints on how it might do memory access, for example. In intermediate representation, what we're going to do is abstract away from those hardware-specific details, and we attempt to make it language and machine independent. So it's independent of the programming language that you're writing a compiler for. It's also independent of the underlying hardware to a large extent. Most of our CPUs nowadays look very similar to each other. They all share the same von Neumann architecture, right? It has registers. We move information from memory into the CPU. We run instructions and then store the result back out to memory. Instead of a very specific intermediate representation like LLVM, for these slides, I'm going to use a fairly high-level abstract notion of intermediate representation. It's one commonly used called three-address code. And as we said, it's a high-level assembly language. Instructions operate on named locations. These are locations where we're going to store some data, and we can pretend we can make infinitely many of them. Although we know that there are limited resources on real hardware, we're going to assume we can make as many of these locations as we want. Eventually, what we will do is deal with the finite number of registers in the hardware by doing register allocation and moving data from memory into registers as needed. But that's a separate step. We're going to do register allocation as part of like code optimization lecture notes. The other thing that you can do is assign a label, and a label is just a target for a go-to statement. You can also have global variables, which are referred to by a global name. As we've seen, these global variables are stored in a separate memory location and can be accessed anywhere in the code. The labels are generated as needed. Anytime we need a target for a go-to statement, we can generate a label. It's called three-address code because there are at most 3 addresses or locations in each instruction. So for example, if I have x equals y up c, the x, y, and z, each of these are locations, and they're at most 3 of them. They could be less than 3. In some cases, you could have a unary operator, for example, or any other such instruction, but we have a maximum of 3 locations that can occur in each instruction, and that's why it's called three-address code. So the address or locations can refer to names or labels. Like I said, the target of a go-to statement. A location can be a constant, like you can have a value that doesn't change, but we still need to save it somewhere. And there are temporary variables that we often need to use if you have a complex expression. Then you need to decompose it. And often, in order to make it three-address code, you need to use lots of temporary variables. If you have 2 different operations, then you have to sequence them in such a way that you're only doing one operation at a time. Let's look at some examples of three-address code to warn you that in these slides, for simplicity, we will omit the type of the address or location. If it's an integer or floating point, etc., I just won't show it explicitly in these slides. And this is just to avoid too much material on each slide to make it less dense, more simple, and easier to understand. In a real IR like LLVM, the type and even alignment for each location has to be defined. The simplest kind of three-address code are instructions like assignments to a variable or location like x equals to y op z, where op is some binary or logical operator. And you can also have unary operations like x equals up y. For example, a unary minus might take a value that's been computed and stored in a location y and then apply the unary minus to it, and the result of that goes into x. You can copy a value, so the copy of the value of y into x is shown here in this copy statement. You can also have jumps, so branches, an unconditional one, which is just a goto. So it doesn't check anything, any variable, it just does a goto. You can also do conditional jumps. For example, you can do if x go to L. So it checks the value, a Boolean x, and then depending on whether it's true or false, if it's true, it executes a goto to a label L. If false is sometimes useful to reduce unnecessary goto statements, as we'll see later. And here, if the Boolean value x is false, then it goes to a label. Another common thing is to have more complex operations. So this would be supported by some IRs where you can compute the conditional as part of the if statement. But typically, we would you compute this x relational operator y, and we store it in C, and then we would do if, we basically would reduce it to this kind of statement. A strict 3-address code IR wouldn't allow a statement like this one because you can convert it into a statement like that one. But some IRs might there's a lot of different intermediate representations out there. Some of them might let you do this because in this case you have 3 addresses, right? You have a goto and then 2 of these x and y that you're comparing. Other types of instructions are function calls, like you can call a function. In some intermediate representations, you have to lay out all the parameters to the function first, compute them one at a time, and then call the function p, in this case, with n arguments. And it takes these n arguments from here. There's exactly n arguments computed there. And this is a way of saying that each argument has to be computed first, and then you do a call to that function. In LLVM, this is simplified a little bit by using the call command, which calls this function p, and all of the variables are just listed over here. In LLVM, of course, each variable has to have its type associated with it. It's either I32 or whatever it might be. And we also have to list the return type of this function p. We're going to simplify it and not use the types in the slides to come. You can have a return statement where you return a value, and you can also save the return. So when you call a function p and it returns something, so let's say the return type was I32, then you can save that return value into a variable or location y. There could also be a void return, so in which case there's no need to save the result of the function call, so we would just ignore it and not assign it to anything. More complex assignments that involve indexed assignments like arrays. So you might need to look up the memory location. So if y is a pointer pointing to some memory location, then it would go and look up the ith location here, take this value and assign it to this location x. Similarly, you might want to put something into, so this was y. If I have x and I have an array, and this is the ith location in the array, you might want to insert a value into that ith location. And that's what's done over here. You can also look at the address of a location. So where is this stored? You might want to save the actual pointer into a variable and do pointer arithmetic. It's possible in assembly language and intermediate representation as well. And you can also do pointer assignment. So if y is a pointer, it looks up the value at that memory location, which is done by this star over here. And so it dereferences that memory location, takes the value out of it, and then assigns it to a location x. Similarly, you can, if x is a pointer here, you can take the value which was stored in that memory location and replace it with a new value, in this case y. So let's look at the core concepts of intermediate representation. So now we've covered all the basic instructions you can have. how do we chain them together into a meaningful program? And in particular, we want to be able to do this while we deal with control flow, if statements, for loops, while loops, etc. A basic block is just a sequence of statements. So just the 3 address code statements that we saw before, just chained one after the other. And they might have function calls, and the functions transfer control from one place, a caller, to another, which is a called function. And other examples include any place where there are branch instructions. So anytime you have a goto statement or a conditional goto, is going to define a sequence of statements that you can enter in and leave, right? It's similar to a function, except it's not always a function call. Sometimes you build up a sequence of statements and you need to target it using a goto statement. We'll see lots of examples of why you would need to do that. Code generation should create the code for basic blocks and branch them together. So essentially, you're creating these basic blocks and then connecting them up. So let's look at some examples of basic blocks and how they are linked together. So let's take a very simple while loop here. Well, it's not that simple because it has a array dereference here. So it's looking up the ith element of this array A, is checking if it's less than V, and then incrementing I. So if you look at this code over here, this is the intermediate representation for that while loop. So you can see that it's first assigning t1, which is a temporary location, the value of I. It's looking at the location in memory where the ith element would be. So assuming that there are 8 bits in a byte. And then it's dereferencing at that location. So T2 is where I need to dereference this array to get the value out, which is T3. And then it checks whether T3 is less than V and assigns that value to T4. In this case, the while loop would look at the Boolean value of T4. If it's true, it executes this part. If it's false, it goes to L2, the statement after the while loop. And then there is a goto statement here, which goes back to L1. So all the way back here to L1, and it says, well, let's recompute A of I, because I is changed. As you can see that I got incremented. So we look at the next memory location, we check if it's less than V, and execute this while loop. So the while loop is set up using this goto statement and this goto statement over here. All of our control flow would look something like this. Okay, so now that we have seen the sequence of instructions that you need in 3 address code, let's group them up into, so in terms of implementing 3 address code, here you can see that I have locations set up, which are the targets of these goto statements. The other way to do the goto statements is, instead of having named locations or labels, these labels are implemented using position numbers, because you can think of each of these instructions is laid out in memory one after the other. So you can think of this 100 as the pointer to the first instruction, and then 101 is the pointer to the second instruction, and so on. And so when we add new instructions, we increment it using the position numbers, and that makes it a little bit easier to implement in some cases. Although this one is conceptually a lot easier to think about and is the kind of intermediate code that's supported by LLVM, right? We don't have to define any position numbers in LLVM, for example. But some older intermediate representations forced you to have goto statements like this one, which were based on the position numbers and the gotos to those position numbers. In the end, of course, when it's in assembly, this is kind of what it looks like when you lay it out in memory, and the goto statement has to go to a certain memory location where then that code is available to execute. Let's look at some further examples of what the basic block looks like. So let's take the same code as we saw in the previous slide, and we generate the 3 address code for it, the intermediate representation. You can see that L2 is something that's targeted by this goto statement, and L1 is targeted by this. But as well, you can see that right over here there is a branch. At that point, the that control transfers to L2. And then this part over here is another segment which is executed. It's jumped over by this goto statement, right? It's executed as a group. So each group of statements here is considered to be a basic block. So that's a basic block. That's another basic block. And then that's a basic block. So we call these statements that are a sequence of statements that you would execute before you do a branch somewhere. So these are, each of those boxes represents one basic block. And if you look at it graphically, instead of the goto statements, you can lay out the goto statements visually. So if it's false, if it's true or false, it ends up in a different basic block, as you can see here. If it's true, it executes this part over here, which is the target of the if true label. And you can see here it's adding 1 to I, right? This is the if true part over here. So this part corresponds to this code over here. And there's a goto to L1. So at the end of this, it goes back and executes this part of the code, checks whether the conditional is true. If it's true, it again goes down this path over here, executes this again, goes back, and so on. At some point, unless it's an infinite loop, at some point it's going to become false, in which case it goes to the statement after the while loop. So L2 would be all of the statements that come after. You can see here, each of these is my basic block here. So each box here is a basic block that I need to, and if I put these basic blocks together with these arrows, that's called a control flow graph. Intermediate code generation for a function. So when I have a function, I would set up the parameters first, x and y, and then I have a label that represents the initial point where I'm starting generating the intermediate code or, statements for this function. So I call, typically the convention would be to call that label the name of the function. And then it executes each of the translation of this high-level program into the low-level intermediate representation. Now in this case, it computes whether d is greater than 0, right, over here. As you can see, T1 gets assigned to D. It checks whether T1 is greater than 0. T2 is a Boolean location that we check, and if it's false, we go to L0. And if it's true, we execute this one, which is this code over here. Translated, it calls GCD with these two variables, D and Y. The value is stored in a temporary, and then it returns that value T3. So as you can see, this corresponds to these statements over here. And then the rest of it, all of these statements are not yet shown there, all those statements that would appear here. So the advantage of the if false over there is that it avoids some redundant goto. So if I was checking whether it's true, and then I would execute this part over here, which is if true, then if it's false, I need to fall through and do a goto to L0, and the L0 would be a separate label. So you can see here it is avoiding a goto after a goto, right? One after the other. In this case, there's only one goto, and then if it's true, it just falls through and executes this basic block over here. Is the notion of short-circuiting Booleans. And this is something you're familiar with as a programmer. If I have a more complex if statement where you have not C, and then I'm combining that with B, and finally I'm doing an OR with A. So you can see that the bracketing of this would be something like, because AND has precedence over the OR, you would first compute the not C, which is I'm going to store in T1, which is over here. And then it's B and T1, I store that value in T2. And then I do the A or the result of this bracket here, which is T2. So A or T2, and I store that in T3. And then I would evaluate the Boolean T3 and say, should I go to the if true basic block or the if false basic block? Short circuiting is a case where if I have A and B and C, we know that if any one of these is false, then I don't need to compute the whole expression. So if A was false, then I don't need to check B and C, because I know already that because of the semantics of AND, logical AND says all of them have to be true. So if A was false, then I don't need to really evaluate B or C. So that saves us some computation. So that's one of the main reasons to do a short circuit. So it checks A, and if A was true, it goes to L0. Otherwise, it goes to L4. What we want to do here is L4 here should skip all of the computation that we don't need to do anymore. Right, so the short circuit is happening in these two states. In L0, we would evaluate B, and if B is also true, then we would go to L1, and then we evaluate C, and so on. So if A was false, we go to L4 and bypass all of the evaluation that we don't need to do, which is for B and C. So that's what short circuiting would do for us, is using these go-to statements essentially to save some work in these situations where the logic of AND and OR should tell us how many evaluations we need to do for a complex Boolean expression. Let's look at some more control flow conversion into intermediate representation. If I have a for loop, then the first thing I would do in the for loop is initialize this. So that's what is happening here in the IR. It's initializing I equals 0, and then it checks whether I is less than 10. So that's what's happening over here. It's computing the I less than 10 part, and then the value of that is stored in T2. If this condition holds, that means I have to do the loop. So notice that I'm doing an if false here. So if false means if T2 is false, then I should break out of the for loop, essentially go to this part of the function where there is an implicit return, which is what's happening here. If it is true, we execute the main body, which is I is equal to I plus 1. And then once we're done with it, we have to go back and do the for loop, the next sort of iteration of the for loop. And the first thing we do is we check this condition again, right? Which is what's happening here. And then if it's false, we exit out of the for loop. If it's true, then we do this part again, and so on until we're done with this for loop. Notice it's calling out to this print function, which is the main body of this for loop. It's just printing out the values of I. So if I have an attribute grammar that looks like this, so this is the context-free grammar part, and then I would show you the actions in order to define the attribute grammar. The first action for ID equals E is an assignment operation. So I would look up the symbol table for this identifier and also the location for it, the place where I would store the value, which is typically allocated on the stack in stack memory as local variables are. And we take the code that I want to generate for this. So this is $3, right? So $3.code. Concatenation is just a shorthand over here to talk about taking code from multiple sources on the right-hand side of a rule and then concatenating them together. Essentially, when you concatenate them, you end up with a sequence of intermediate representation instructions, right? Concatenation is just building up the IR for using this attribute grammar. When I have a binary operator, I would create a new location. So I'm just using this shorthand for new temp. This is not LLVM or anything. So for LLVM, you might do something somewhat different. But the idea is you need to create a location for the left-hand side, which is what the new temp is doing. The code that was generated for $1 and $3, right? So $1.code and $3.code. And we concatenate those together. Remember, the order matters, right? You want to generate this code first and then this one, and then generate the code for the left-hand side, which is what's happening here. It says that the left-hand side, so ADDR is just short for like a location of some kind. It's abstracted away for us. We don't care whether it's in memory or in a register. That's going to be handled later when we do register allocation. Now, when I have that addition, I add the two things and I store it into this new location. And notice that that's new location is then returned up up the parse tree, as it were. So if I was to do an addition and then assign it to a variable, this $3 would inherit the location of what's on the left-hand side, like this location over here. Just like with the binary operation, we would do the same thing with the unary operator. Nothing much is different. Again, we are assigning a new location to the left-hand side, which can then further be used when that is used somewhere else in the tree. This rule is always the straightforward one. You just take this location where the value of that $2 is, and then assign it to $. It just inherits that from, except that there's parentheses around it, which helps with ambiguity. An identifier would be stored in the symbol table. So the storage of this identifier is taken from the symbol table and assigned to, again, the left-hand side. That's a $.address is a new location. So it's new code, so that when I generate this new code, I can concatenate. All of these concatenate operations would add information as we generate them. And when we get to the top of the parse tree, we would have a concatenated list of all the instructions that we want to generate for this input program. When we deal with control flow, we have some non-trivial issues in setting up the control flow graph, like linking together those different basic blocks, which boils down to finding the right target for each of the go-to statements. It turns out not to be that trivial to do. It takes some doing. So one way you could do that is to implement these in 2 passes, which makes things easier because all of the targets for the go-to statements have been laid out, and then you would insert the locations, the target locations for the go-to statements. But it's possible to do it in 1 pass, and that approach is commonly called backpatching. That allows you to do 1 pass code generation into intermediate representation. The target labels is the main issue in control flow. And backpatching basically is it's a fairly sort of nice idea. The idea is you generate the go-to statement or jump statements with empty targets. They're temporarily unspecified. We put the statement which has this empty target into a list. When the target is known, once it's known, we fill in the proper labels in those go-to statements or jump statements. So essentially let's say we have a go-to statement that's going to a location further down in the code. We haven't generated it yet. It has to go to somewhere which is like L1 : So we need to generate this go to L1, but L1 hasn't really been activated yet. Like nobody has written the code for L1. So therefore this L1 doesn't exist yet. So what do we do with this? Well, we store this go-to statement. So let's say is in line number 101. We store this line number into a list, and that list is going to be used later. When I get to L1 and I'm generating the code for this, what we can do then is say, let's look at the list where a target is needed. We know that when it's the right time to do that is when I generate this new label L1. We look up in this list what are the different instructions that are requiring a target. So we look up that list over here. We see, I see this statement needs a target, and then we replace this question marks with the L1, and now you have a well-formed intermediate representation. However, some IR libraries like LLVM, we can create multiple locations and set them as insert points. And so what we can do then is essentially create all of the different basic blocks in complex control flow state, like if, for, while loops. We can create these multiple locations and then switch the insert point to insert the instructions for each one. So we can set up the branching first and then insert instructions into those basic blocks later. So let's look at an example. Let's first look at control flow using an IR that supports multiple insertion points. Let's look at a simple if statement first. In this if statement, it checks the condition. a less than b, and then increments I, or it assigns I plus 1 to a variable j. So we start off with the first basic block, which contains the evaluation of the Boolean expression for the condition. The conditional branch happens here. If t0 is true, we want to go to some location. So we don't know where that location is yet, so I'm going to put question marks there. So we know that there is a if true part and there is an else part over here. As we saw in LLVM, you can figure out which is the location where we want to insert these statements. And then we create a new basic block called if, which is what's happening here, right? This if is what's created here. And then as soon as you create the branch, it does a goto into that branch. So that's what this create branch is doing. It's just saying start by executing this if block. What do we do when this is true? If it's true, we should execute the if true basic block. So the little bit of LLVM code that it's a little bit abstracted out. It's more like pseudo code for LLVM. Is you would create capital C here, by the way, is the context in which we are operating, which we typically put into a global variable called the context. And we're creating a new basic block with a label called true. And we enter this into the symbol table. And you can see the reason for that shortly. It's convenient to store this information about the basic blocks in the symbol table. It makes code generation for certain other aspects of control flow much easier. And the next thing we do is we set the insert point. So whenever we're ready to generate code for this part of for this basic block, we have to set the insert point first and then generate these instructions. So here, when it's true, you can see that this question mark is going to be a goto to this label over here, true. So we would replace T0, the goto statement goes to this label true here. If it's so this new symbol table scope has to be specified for control flow statements. And just like with the other use cases for a symbol table, every time you enter a new block or when you're inside an if statement, you want to create a new symbol table just for that scope, for the scope of that control flow for if or for while. For all of these complex control flow cases, what you want to do is create a new symbol table scope for them so that you don't by mistake. So when you're done with the if statement, for example, you would just pop out the symbol table and it doesn't hang around and you don't get a spurious goto statement, for example, later on. So the symbol table has this nice property that once you leave a block, or in this case, leave the if statement, you can pop out the symbol table and all of these different labels that you're storing using this enter symbol table command, all of those labels would go away. Okay, so the next step is what do I do with this goto to what? Well, it has to, if you think about once it's true, it should start executing the statement that follows after the else, right? So we call that the end. That's the end of the if statement. And we insert it into the symbol table as the end. And we call this the end basic block. And then when you're ready to generate code for it, we would set the insert point to that. In this case, it's not doing much. There's just all of the instructions after that are listed as starting from end. Now, this is what happens when it's true. What happens if it's false is we create an else block. We call that else. And here I'm calling it the if false basic block. You can also think about it if the same idea applies, obviously, whether you have an else statement or not. In some cases, you might just have an if then statement, right? In which case, this false would end up going all the way to the end because there's no else statement. If false would end up going to end because now you can start doing the statement after the if. So in this case, the else is doing j equals I plus 1. So you can see here, this is computing I plus 1, and then this is assigning j, the value of I plus 1 to j. Now, once I'm done with this, I need to go to again. And in this, you know that we can just fall off the end of this else into the end. So we would just connect up else basic block or if false basic block directly to the end basic block. And you can see that an if statement is conceptually fairly easy, but when it comes to intermediate representation, you have to keep track of the different basic blocks for the if then else statement. And you have to keep track of all of the different places where you can insert statements. Like in this case, I can insert statement at the if, the true, the else, and the end. Let's look at a question that you can answer to make sure that you're understanding. What would be the go-to target for a break statement in either the true, so either here, so instead of I equals I plus 1, let's say that I had a break statement here. So as you know, a break statement breaks out of the loop. So where would it end up? That's one question. So the other place you can have a break is in this basic block. You can have it in the else. And so the question is, if you have a break statement, right, you jump out of the loop. And so, not the loop in this case, sorry, the if statement. You want to jump out of the if statement. So it's fairly straightforward. You can figure it out that if instead of incrementing something or doing any of these instructions, if I did a break, all I would end up with is breaking out of the if statement and ending up in this position. And the same thing here. Like if I have a break, I would also end up in this position, right? Because that signifies the end of the if statement. Let's look at a while loop next. So in this case, we are checking whether I is less than n, and then incrementing I, and just doing this repeatedly in this while loop. So the first step is to set up the conditional branch. And in this case, I is indeed less than n. It's going to go to some place. We don't know which place yet. Well, it's either true or false. So just a peek behind here. In this case, it's very similar to the one before. It's a small typo here. This would be creating a loop basic block, and then it would be creating a branch, so it would branch into this loop. If it's true, I would end up creating a new basic block called the body of the while. So that's what it's called here. And then it sets the insert point for this body basic block and starts generating these instructions here. So if this go-to statement, now we know what is the location for this go-to. It targets a label called body. So here I would put in body. At the end of it, since it's a while loop, I know that I should do a go-to back and do the evaluation of this conditional again. So that's what happens at every while loop. You're going to check the condition again, and if it's false, then you exit out of the while loop. So here we know this already. This go-to would be go-to loop. If this was false, we would create a new basic block called end. It doesn't have any information because it's all of the statements that follow the while loop. And in this case, you can see that there is if it's true, it goes to the body, goes back to the loop, checks again, this conditional goes through the loop again, and goes back to this position. At some point, if the condition is not satisfied, so I is greater than or equal to n, for example, in this case, it would go to the end block here. So you can see there's the while loop is captured nicely in these three basic blocks. There's a loop through the body as many times as needed, and then it would check the condition and then go to the end block when it needs to end it. So one question is, what would be the go-to target for a continue statement in this body? So instead of these statements, what if we had a continue? Remember that a continue is something that would go back to the start of the while loop. As soon as it sees a continue, it's going to go back to the start of the while loop. You need to make sure that that doesn't result in an infinite loop, of course. Let's look at control flow for for statements and a for loop. So here we have initialization part, I equals 0, the conditional check, and then the post condition, which is to increment I after we do the body of this for loop, which is this one. So we start with the init. Right away we are initializing I equals 0. It's going to go to some location. We haven't figured it out, so we need to set up where it's going to jump to after the initialization. Well, we need to create a loop. So here again, I would call it loop basic block. That's a typo. So in this case, it would create, that goes in there. It would create a new basic block called loop. And loop is just going to check whether the conditional aspect of it. So if it has to check first before doing the loop whether the condition is satisfied. Is I less than n? If I is indeed less than n, then it would have to go to another location. So if it's true, we would end up with the main body of the for loop, which is that one. We call that the body basic block. When we're ready to generate the instructions, do the code generation for this, it would set this insert point here. As you can see, we can set up these basic blocks and then set the insert points as needed when we needed it. So in this case, we have body. We are just doing an assignment of I into this location C, and then it does another go to. Now, where does this go to happen? At the end of this body, we need to go and check this condition again. Oh, sorry. First thing we do is we do the post condition. So we need to, at the end of this body of the for loop, we need to first execute the post condition, which is going to be generated for this go to. Before we do that, let's see what happens if this condition was not satisfied. Then it would take this branch over here. It would create the end. So essentially end is over here after this for loop. And the end basic block is there to exit this for loop. Okay, so going back to computing the post condition, which is the next. So we call it the next basic block. There's a few typos here. Sorry about that. That should be called next BB. And when I insert that into the symbol table, and then I can set the insert point for this. So this should be next BB as well. We do the increment. So this is doing the I equals I plus 1. Once I'm done with I equals I plus 1, I should go back and check this condition again. So I would go to loop here, and I would go to next over here. And when I'm done doing the post condition, incrementing I go back to the loop. So a good question would be, if you're in the body block over here, two things you can work out is break. So break would break out of the for loop, and continue will go back and do the post condition and then do the check. And then if the check is true, we would execute the body again. So break and continue sort of play with the control flow. Essentially, they were introduced as a way around the goto statement being used in programs. So break and continue help you break out of loops, etc., without having an explicit goto statement. But when it comes to the intermediate representation, we still do need to generate the goto statement. Let's look at an intermediate representation, which is somewhat different from LLVM, that only supports line numbers. How do we do these control flow cases in that case? We're going to use this idea called backpatching. And the idea is we keep these question marks until we have generated all of the intermediate representation. Each line of intermediate code is assigned a unique number. So that number will be the target of the goto state. 100 is a line number which is missing a target, right? In this case, it's the target. We're going to keep these lists separate. So this is called a true list because when it's true, it needs to jump to that location. So in this one is the false list because if T0 was false, that's the outcome we want to end up in, right? So if it's false, then maybe it has to go to the else part in this case. finally, if it's a loop of some kind, then you might want to go to back up to the top of the loop, for example. So the next list is a way of determining what the next action should be. So what we're going to do is store these sentence or locations for the intermediate representation. So 100, 101, and 105. We're going to store those into these respective lists. So this one would have 105 in this one, 101 goes into this list, and 100 goes into this list. And then when you're roughly over here, you've seen all of the locations that you need. And then I would execute these backpatch instructions. And I would say in code location 100, I would go to this go-to statement and replace it with 102, because that's what happens if it's true, we need to execute the body of this if statement. The false list here is when the condition was false, it would end up in this part of the code, right? So that's why this one would result in go to 106, start here, which is this else part over here. And finally, last is the next one here, which is in a while loop or a for loop, it's going to go back up to one of the previous locations. But in this case, for an if statement, the next list will contain the next statement, which is 109. So we will just replace it there. So we maintain a list of statements that need patching by future statements. That's why it's called backpatching. And there are 3 lists maintained: a true list for targets when the evaluation is true, a false list for targets when the evaluation is false, and a next list which ends a block or is also used for loops. And these lists can be implemented as a synthesized attribute. And often what we'll do is introduce a new non-terminal called M, which is called a marker non-terminal, and it just derives the empty string. The only reason for this marker non-terminal is in order to create one of these lists. So you might create a true list in the right place or get the location of the subsequent block that's in this context-free role. So by adding this marker non-terminal, it gives you a convenient place to add some extra code gen bits that you need, which you can't directly do in any one of those things in the right-hand side. So for example, if I have a Boolean, then I would execute a block. This M over here is a marker non-terminal. As you can see, it just derives epsilon, so it looks syntactically useless, but semantically it's useful because it's representing the instruction that happens here, the first instruction of that block, which is useful because if this Boolean was true, then you have to start executing from this position over here, which is what the M or the marker non-terminal is giving you. So in this case, we have code that generates, it's sort of written here in shorthand, just as string. We're just creating a string which contains a 3-address code, intermediate representation. The key thing is that we don't know the targets of this go-to statement. At the time when I'm reducing this rule, some kind of operator in E, when I reduce this rule, I don't know what the target of the go-to is, right? So in this case, I want to evaluate that Boolean and then jump to this location, or to leave the if statement altogether if it's false. So let's look at generating the code. So if this is a concrete example of an if statement, let's just work through this actions for this attribute grammar. So first I check if A is less than B, which is this statement over here, and storing the Boolean in a location called C. So that this part over here is generated by, so this part generates this. Now, when I add the code for if C go to someplace, that's added over here. Finally, we have an unconditional branch, and this unconditional branch is acting as where do I jump to if the condition was false, right? So this is for true, and this is for false. If I have a true list and a false list, you can see that 102 and 103 are both in it. 102 is in the true list because it should target a go-to location, which is what this body should be, right? This I equals I plus 1. So essentially the location of that. On the other hand, 103 is in the false list because that's the location you need when the condition was not satisfied. The marker non-terminal over here returns the first location of this block over here. When I have that, this is computing the I equal I plus 1 over here. Once we have the M instruction, this M calls this rule, which gives me the next instruction. The next instruction is 104. I can backpatch now in this location. I know that this is, when it's true, I should start executing over here. So this backpatch takes care of that aspect of the control flow. The next list for S over here, for this would be 103, right? This would be when it's the condition is false. And the backpatch there for the false list would be to take 103 and introduce a goto statement. So in this case, the goto statement would insert a goto to 107, which is way after, or not way after, the next statement after the if statement over here. So it's a little bit more complicated than LLVM. LLVM is definitely much easier to use. But I think it's worth looking at some of these older intermediate representations with each statement having a number, just because it was good to review that. So when I have this while loop, which is while I less than n, and notice that it's doing continue. Continue means go back and do this. And this is definitely an infinite loop in this case, but it's a simple case. And obviously the use of continue is going to happen if for example, inside the while loop, there was an if statement and then did a continue. But in the interest of saving, time and space on the slides, this is going to be the simple while loop that we try to generate code for. So you have the condition, which is the Boolean I less than n. And we already have reduced this m goes to epsilon. And so I know that the value of the location is 101. The next step is to generate the code for the while loop, which says, if it's true, then where do I go to? And if it's false, where do I go to? So let's compute the next step, which is so we've done that one. Now we're interested in the start of this block. So what we're going to do is create a new instruction 104, and then the next list is going to be in this block over here. That's $7 over there. And the next list there is going to be 105, which is the next layer. So in this case, this part, which is the main, this loop over here, this continue. So this is the continue statement. And this is 102 and 103 are the conditional statement. So if C, we want to go to some location, it has to be 104 because in this while loop, it's checking that condition. And if it is true, then it goes into the body of the function, of the while loop. If it's false, it ends up with the part which is outside of the for loops. So we backpatch 103 with 10. So this line over here, this goto statement goes to 105. And so that takes care of the conditional, whether it's true or false. And the continue statement here, if I have continue, it takes it back all the way to the start. So in this case, the body is just going to go back to the start. It does a check again and then repeat. However, in this case, when I'm generating the code for continue, I'm over here. So in this case, what I would want to do is either look up the symbol table for these values or, devise something in the attribute grammar to do it. It takes a little bit of trickery to do it correctly. So in this case, the trickery just is these lists of things, right? The trick is using those lists in order to get where you are. We also saw the case earlier of using the symbol table, and that would work here as well, because as S goes to continue is going to generate this go-to statement. The question is, what is this go-to statement going to resolve into? And that can be then stored in the symbol table for use. And then when this loop is done, it would essentially go, that symbol table will go out of scope and you would pop it out from your list of symbol tables. Finally, let's look at the case of, we looked at continue, let's look at break. So it's everything else is the same, so we can go a little bit faster. We check for the condition. We know that this first instruction is part of just before this conditional check. If I is less than n, right, that's a condition. It goes to some mysterious location which is not yet been generated. We compute the block. The block instruction is 104. And we take, so this case over here, the block break list, which is S, this S over here has to be assigned to the block. And the block break list, which means where would you go if you wanted to get out of the while loop, would be 104. 104 is what it's going to do is store this 103, 102, and 104 into one of these backpatching lists, the true list. 102 goes into the true list, 103 gets into the false list, and then the break list is stored as well, which is 104. And what we're trying to do here in this case is to model the break. So break just means get out of this loop and continue with other things in the program. So what I'm going to do is assign the value of so $2 here is this one. If we want to get the different targets for this, so we know that if it's true, we should go into the body, which unfortunately has, so this would be the break statement that's in line 104. 103 and 104 both get the same target location, so you can see here. So that's, if it's false, it's going to end up over here. And if you break, you end up in the same place, right? So break and continue are special purpose instructions that mess with the control flow in useful ways. Continue goes back to the top of the loop and break just exits out of it. Array elements are a little bit tricky because they need to be, the arrays are not native to the CPU. So we need to execute some arithmetic to get at the array element that's required. So if base is the address of the storage allocated for the array, so hopefully you can get its malloc status, the address of the storage allocated for the array. And then the ith element AI begins in the location base. So this is I times W, which is the number of instructions that, so I times W will tell you how far the offset would be. And then we add base. So that gives you the precise pointer that points to AI. And if you have a two-dimensional array, then it's just a slightly more complicated arithmetic that one has to do. So you have to do I times n plus j, and then the whole thing times w. Right? This would deal with essentially you're flattening out a two-dimensional array into a very long one-dimensional array, and access to that can be done using this form. When you're dealing with array references, there's a few things to be careful about. So in this example, we're taking some right-hand side, which is you're looking at array location 0, multiplying by 2, and you're supposed to insert it into the array location 1. If you look at the left-hand side versus this right-hand side, intermediate code representation, the first thing we're doing is looking up, so T3 would be the pointer that we compute for array of 1. And then if you look at what's happening here, it's dereferencing that location and storing the value at that location in T4. And at the end, it is assigning so T11 is essentially, this over here would be the array of 0 times 2. By the way, I think here I would replace these 4s with an 8 for a more modern architecture. Instead of 4 bits, 8-bit width for an int is more suitable for modern machines. So going back to this, we've computed array of 0 times 2, and now we want to assign it to the L value. And if you look at what the left-hand side is doing, it's assigning it to this T4, which was prematurely dereferenced over here. Whereas on this side, you can see that T3 was computed in the same way as in the left-hand side IR, except that we didn't dereference it here. So we've removed this line from this right-hand side IR. And at the end, when I'm ready, I've computed array of 0 times 2. I've computed that value. I want to store it. I have to dereference the pointer and store the value inside the pointer that's given to us when we computed array of 1. Like T3 contains that pointer. So dereferencing the pointer is really important. So that's why this one is the correct one and this one is the wrong one. If you have recursive functions, you want to make sure that you are doing the recursion correctly. So you're calling the factorial and you want to call it with the right value. And in this case, you would have a recursive function call, right? So if you wanted to compute this n less than equal to 1, in some intermediate representations, you don't have less than equal to as a native operator. You have to combine it by using less than. You first do less than is n less than 1, and so basically a logical and with n equals. So we do less than and equal to, which is of course the definition of less than equal to, right? So in some cases this is okay, this is allowed. In other IRs you have to decompose less than equal to using Boolean logic. So you have to do less than and then equal to and then do an or of less than or equal to. So this is something that's useful when you're computing more complex Boolean expressions. And yeah, that's sort of recursive functions are fairly straightforward because the intermediate representation takes a lot of the burden off the hands of the compiler writer. Let's take a look at some ways of implementing IR in a machine. So like the memory model, storing it, etc. You can store it as quadruples. So you have all of the operator as one column, arg1 as a second column, arg2 as a third column, and then the result. So here's 1, 2, 3, 4. So that's what gives them the term quadruple. It's 4 things. So that's one way to store it. Another way to store it is using triples. We store the location separately. So in this case, we have the operation arg1 and arg2, and instead of using for sort of extra information, what we're going to do is essentially we're pointing to the previous or another location using this number. So essentially we compute minus c. The result is stored. It's a little bit like cheating because you could think of this as an extra column, but really it's the index of that minus c operation. And notice that instead of storing it at a different location, it just uses the index of that operation. And similarly, if I have, so that's minus c first and then b times minus c, then I do a minus c again over here, which is number 3, and then b times 3 again. So that's doing the same thing twice. And then I can do a 2 plus 4. So a 2 plus 4 is a b times 1 and b times 3, which is b times minus c and b times minus c. We're going to add those two together. And again, we're going to use the location. So this location 2 and 4 is where the result is going to be stored. It's almost like a pointer to the result. And so this leads to a little bit of a tree structure. In fact, in GCC, what they have in contrast with LLVM is a more tree structured intermediate representation. And this result is identified. The result is identified by the position instead of storing it into a new variable. And the advantage of this is that the code optimizer can easily change the order of the instructions, and everything else would stay the same, right? Because if you reorder it, you just point these things to the right location, and you don't have to regenerate or redo any of the go-to statements or the location values and the names, etc. By having this location or the position of each operation makes it a lot easier to reorganize. Another idea in implementing this IR is you use the same idea as the last slide, and we have indirect triples. So again, the same idea as before. These indirect triples can then be stored using an instruction list, which can be reordered. So this allows a more flexible representation. Finally, we have static single assignment form, which is one of the more important intermediate representation formats. For one thing, LLVM uses it, but also it has various beneficial properties for both for code generation and code optimization. The basic idea behind SSA, or static single assignment form, is that on the left-hand side, instead of a variable that can be used twice, the variables can only be used once. So this will be assigned to A1, and then this gets assigned to A2. So notice that A1 and A2 are different locations, and the variable A is never reassigned. So you always are assigning, when you do an assignment, like in this case, you're assigning to A1, instead of reassigning to A1 again, we are assigning to a new location, A2, and then using that location for subsequent uses. When it comes to intermediate representation in general in writing the backend code, we have to make sure that correctness is addressed first instead of efficiency and optimization. Because efficiency and optimization are a secondary concern. The first concern should be that the code is correct. And we don't want to really try optimizing things too much at this point because it can come at the expense of correctness. So in summary, we saw 3-address code, which is an example of intermediate representation. It's close enough to machine code so that the subsequent translation into assembly is fairly trivial. The advantage of an intermediate representation is that we can ignore some of the complexities in computer architecture, such as limited registers or multiple instructions, branch delays, load delays, etc. And even register allocation is something we can ignore in intermediate representation. The advantage is not just ignoring these complexities, but a lot of code optimization can be done on intermediate code, on intermediate representations. And that makes it more portable to have these optimizations that can be used across many different machine architectures instead of writing a special optimizer for x86 and then another one for ARM, etc. You can get away with a single optimizer for a lot of different machine architectures. Next, we're going to look at static single assignment in more detail, because that's quite important given that LLVM implements that. So we're going to start with a brief intro to static single assignment.